Hi, these notes are available as PDF for today. At the top, you see the same problems that we worked on the board just yesterday. I went ahead and filled in the answers for reference, and you can see the work by watching the video. The last problem in the big red square here is the one we did on the board, and I show the steps that we showed on the board in that first column. That's where we basically did it a little bit at a time, from the portion that's the closest to the center, the most nested, and worked outwards. I replaced B bar or B complement intersect A with just the number 8, then took its complement, all that's the numbers all 1 through 9, and so on. We ended up with the empty set. Here's a couple of other ways in the other two columns. So these use properties of the complement, unions, and intersections. First there, I see an application of De Morgan's laws. Remember that you have, when we take the complement of an intersection, you can apply that complement separately. So at the bottom of the page here, I have listed out the various properties, laws that we've used. There at number 3 is De Morgan's, and there are both of them. There's the complement of an intersection and the complement of a union. So you break up the complement and you flip over, the intersection becomes a union, or the union becomes an intersection after you break them up. And yes, these are exactly the same laws as we know for the negation of the and or the or statements, just applied to sets. So anyhow, back up in the center column of the problem, I worked it out by first applying the De Morgan's laws for a union, then or for an intersection on the B bar intersect A, and then I applied the De Morgan's laws for the big union. I used them as much as I could here. Then eventually I had nothing but intersections left. Now, property of intersections that I put down at the bottom of the page here in number 5 is that intersections are associative. If you have several in a row, it doesn't matter which order you apply them in. So A intersect B intersect C, it doesn't matter where you put those parentheses. Same for unions while I'm there. A union B union C, doesn't matter where you put the parentheses. So in the problem, it didn't matter that I had parentheses at the end. I could just take them out. And then I noticed that I'm looking at A intersect A bar, or A bar intersect B bar intersect A. But since intersection is commutative, we can move those around, and I see A intersect A bar. Now that, there it is in number 1 down below, is the empty set. For any set, its intersection with its complement is empty. You can't both, an element can't both be in the set and not in the set, so it's empty. That one took a little bit of time, just as many steps as the previous method. The third method there is even a little bit faster. That's where, after applying that De Morgan's law on the intersection, oh yeah, and I forgot to mention that after applying De Morgan's laws, I looked down at the bottom there, number 4, and noticed that the complement of a complement is back to the original set. A bar bar is equal to A. I use that on B in this problem. B bar bar is equal to B. So I looked at the A union B union A bar, and since union is also commutative, we don't have to worry about B. It contains A union A bar. That, of course, is the whole universe. There it is in number 2 down at the bottom. Whenever you take the union of a set with its complement, you've just collected everything. So that gives me U bar, and the complement of everything is the empty set. So why do we need 3 ways to do the same problem? In fact, there's probably more ways to do the same problem. Not really necessary except for educational purposes to demonstrate things. But one possible plus is that you can do it 2 ways and check your work. If you're like me, the first time I do it, a lot of times I make a little mistake. So if I try it a different way and get the same answer, I'm much more confident. Good place to stop.